Hey everyone, welcome back to the deep dive. Last time we took a pretty broad look at the technologies out there for border security. Radar, barriers, the whole range.
We did. And we saw some impressive stuff, definitely. But the big challenge, as always, is deploying it effectively, especially across huge, tricky areas without, well, costing a fortune.
Exactly. So this time we're really drilling down into something specific, a proposed design, really a blueprint for a large-scale system that aims to be both effective and surprisingly affordable.
We're talking smart sensors, AI power, building on those techs we discussed, but aiming for less than, what, $500 a unit?
That's the target, yeah. A sub $500 unit cost.
Yeah.
But a huge network, always on, for that kind of price point per sensor.
And the key is where it needs to work. The
Right.
sources mention places like the dense forests in western Kashmir. I mean, just picture trying to keep watch there.
Yeah, terrible visibility, extreme weather sometimes. Just really, really challenging to have any kind of constant presence.
So you need something persistent. You need detection that works day and night, rain or shine.
Which brings us to the must-haves for this proposed design. First up, detection range. Needs to be decent, even in forests, say 100 to 500 meters.
Right, 100 to 500 meters, even with forest cover.
Yeah.
And as you said, 247 all-weather operation, that's critical.
And since they'll be out in the middle of nowhere, they need their own power source. Autonomous power.
Plus, secure comms to get the alerts out, probably satellite given the remote locations.
And the absolute linchpin, the thing that makes it viable, is that low cost for mass deployment. We're talking potentially millions of these things.
Millions, yeah. And easy enough to deploy. So, okay, let's get into the nuts and bolts. The proposed solution, it starts with a dual sensor approach.
Dual sensors. That sounds smart right off the bat. More reliable.
Definitely increases reliability, reduces false alarms, hopefully. So the first part of this duo is a thermal infrared camera. LWIR, long-wave infrared.
Okay, thermal, so it sees heat, basically. What's the big advantage there?
Exactly. It sees heat signatures, like people. So total darkness, not a problem. It doesn't need any visible light. The sources suggest maybe a 200-meter range in forests, could be up to 500 meters in clearer areas. And that's with a pretty standard thermal core, like a 320 by 240 microbolometer, maybe a 15-20 millimeter lens. Nothing too exotic, cost-wise, at scale.
So sneaking past in the dark isn't really an option against this.
Pretty much no, and it's also harder to fool with standard camouflage. It sees through light fog, gaps, and leaves. It's looking for that heat pattern.
Okay.
And the clever part is adding some processing right on the sensor itself. AI algorithms, maybe, looking for human shapes or specific thermal patterns.
So it's not just sending raw video.
No, definitely not. That saves power, too. It
Yeah.
can run at a really low frame rate or even sleep until something triggers it.
Ah, the trigger. That leads to the second sensor, right? The motion or presence detector. What's its role?
Its main job is to be the super low power watchman. It's always on, using almost no energy, just scanning for any activity.
Yeah.
When it spots something, then it wakes up the thermal camera.
Got it, like a tripwire. What kind of tech are we talking about for that trigger?
Well, a few options mentioned. One is passive infrared, PIR, like in security lights or trail cams. Detects heat changes, range maybe 30 meters or so.
Okay, common stuff.
Yeah. Then there's mmWave Doppler radar. Think 24 or 60 gigahertz. This is more interesting. It sends out tiny radio waves and looks for shifts in the returning frequency of the Doppler effect. Detects movement.
And the advantage of radar?
Potentially longer range, maybe 100, 150 meters if you push the power a bit. And crucially, it works better in fog and can see through light foliage. Huge plus in forests.
That does sound much better than basic PIR for this kind of environment.
It could be. And the third option is seismic. A geophone basically listens for footsteps, those tiny ground vibrations. Range, maybe 30, 50 meters for a person, depending on the soil.
Listening to the ground.
Interesting.
Interesting.
And what's really smart is potentially combining triggers. Like maybe it needs both seismic and PIR detection before it wakes the camera.
Double check. To cut down on false alarms from, like, animals or wind?
Exactly. Reduce those false positives. And these trigger sensors, they use microamps of power. They could potentially run for years just sipping battery power.
Years. Wow. Okay, so the trigger fires, wakes the camera. What happens next? Imaging and processing.
Yep. Camera snaps a picture or a short video burst. Then that data goes to an onboard processor. And these aren't wimpy processors anymore.
Right, you mentioned smartphones earlier.
Exactly. We've got powerful, low-cost chips now, thanks to that industry. Things like Qualcomm Snapdragons, Google Edge TPUs. They can run complex software right there on the device using very little power.
So the sensor itself is doing the thinking.
A lot of it, yes.
Yeah.
Filtering out non-threat movement, identifying human shapes in the thermal image, maybe even telling humans from large animals. Deep learning algorithms are getting really good at this, even on thermal data.
And the benefit of doing that on the sensor. Edge filtering, you called it.
It's absolutely essential. You don't want to swamp your satellite link sending alerts about swaying branches or deer walking by.
Right. Especially with potentially millions of sensors.
Precisely. So the sensor decides if it's a credible alert. If it is, it might just send a tiny text message. Human detected at these GPS coordinates. Maybe a small thumbnail image.
And then someone back at base can decide if they need more.
Exactly. They could request the full image if needed. It's all about conserving that precious satellite bandwidth and avoiding alert fatigue.
Makes total sense.
Yeah.
Only send what matters.
Mm.
Okay, communications. Satellite seems unavoidable for these remote spots.
Pretty much the only option, yeah. The proposal looks at things like Iridium Short Burst Data, SBD, or similar LEO satellite IoT modems.
SBD, how much data can that handle?
It's small packets, around 340 bytes, enough for that text alert, GPS, maybe that tiny thumbnail we mentioned. Newer services are starting to offer a bit more, maybe enough for a low-res image sometimes.
And how does the signal get out? Big dish?
No, just a small, compact, L-band patch antenna on the unit itself, omnidirectional, which is important.
Meaning it doesn't need careful aiming.
Exactly. Makes deployment way simpler. Just stick it on a tree or in the ground, and it should be able to see a satellite. And naturally, all this communication needs to be heavily encrypted. AES-256 is mentioned, standard strong encryption.
Okay. But satellite airtime isn't that expensive, especially for potentially millions of devices. How do you manage that cost?
That's a huge consideration. The main strategy ties back to that edge processing. Only transmit when you have a high confidence detection.
So most sensors are silent most of the time.
Correct. They're just listening, sensing, maybe checking in very occasionally. This drastically cuts down on the data costs compared to constant streaming or frequent check-ins.
What about grouping sensors? Like local radio to a hub, then one sat link for the group.
That's mentioned as a possibility, a hierarchical network, but the proposal leans towards direct-to-satellite for each sensor.
Why? Seems less efficient.
Simpler, more robust, avoids a single point of failure. If that hub sensor goes down, you lose contact with a whole cluster. Direct link means each sensor is independent.
Okay, reliability over bandwidth efficiency in that case. Got it. Let's talk power. Keeping these things alive out there. Battery and solar.
That's the plan. A combination. A decent-sized battery, maybe 50 to 100 watt-hours lithium thionyl or lithium ion, plus a small solar panel, maybe 10, 20 watts.
The battery runs it and the sun tops it up.
Yep. Battery gives it maybe days or winks of autonomy on its own. The solar panel recharges it. In bright sun, that little panel could generate maybe 50, 100 watt-hours a day. Plenty to keep the system running indefinitely given the low average power draw.
Dense forests, not much sun gets through, right?
Yeah.
How do you handle that?
Good point. That's a major challenge. Couple of ideas. Maybe a longer cable so you can place the panel itself up higher in a sunnier spot while the sensor stays hidden below.
Yeah.
Or a modular design. Sensor unit here, separate solar unit over there where the sun is, connected by wire, or maybe even wirelessly like inductive charging. Adds complexity, but gets you the power.
And better solar cells, too.
Yeah, using high-efficiency cells, maybe multi-junction ones that do better in low or indirect light, squeezing out every possible watt.
So smart placement, efficient cells, and aggressive power saving everywhere else.
Absolutely. Everything off until triggered. Just tiny periodic I'm alive check-ins. Put it all together, and the goal is maybe 5+ years of operation without a battery change, assuming the solar works reasonably well.
5 years. That avoids a massive maintenance headache. Non-rechargeable batteries are simpler, I guess, but not for this scale.
Right. The logistics of replacing millions of batteries would be insane. Solar is really the only practical path for long-term, large-scale deployment.
Makes sense. Okay, physical design. What do these things actually look like? How big are they?
Think roughly hardcover book size, maybe 20 by 15 by 5 centimeters, something like that, plus the panel, camouflaged, obviously. Matte greens, browns, maybe textured like bark or rock. Extremely tough. Needs to meet military ruggedness standards. IMIL STD 810G. Handle rain, dust, humidity, shock, extreme temperatures. Maybe negative 40 up to plus 50 Celsius. Sealed connectors, tough casing. The solar panel might be flexible or hardened glass.
How do you actually put them out there?
Different options. Could have a ground spike, straps for trees. maybe even designed to be dropped from a drone.
Dropped? Wow. Needs to survive that too, then.
Yeah, some shock absorption built in, or maybe a simple deployable drag chute. And anti-tamper features are important.
Like if someone tries to open it.
Exactly. It could send an immediate alert, maybe even wipe its own software. But realistically, with millions deployed, some will get lost or damaged or tampered with. So the design minimizes sensitive data stored locally. Don't make it a valuable intelligence target if captured.
Okay, assume some losses. Finally, all this data floods in.
Yeah.
How is it managed? The back-end system.
Needs a sophisticated backend, probably cloud-based or in a dedicated command center. It collects all the alerts. And again, AI plays a big role here on the backend.
Awesome.
Filtering duplicates. If 5 sensors see the same person, you only need 1 alert, really. Correlating detections over time to track movement. Building that overall picture.
Can the command center talk back to the sensors?
Yes, that satellite link is two-way. So they could send commands down, maybe adjust sensitivity, disable a faulty unit, or request that full res image we talked about.
And location is critical, I assume.
Absolutely. Built-in GPS is mentioned. Each alert is automatically geotagged. You see exactly where the detection happened on a map. Crucial for situational awareness and response.
Okay, let's talk dollars and cents. The cost. This sub-$500 target at scale. How realistic is that breakdown?
The proposal gives estimates based on volume. Low volume, like 1,000 units, maybe $1,200 each. Pretty pricey.
Yeah.
But ramp up to, say, 100,000 or 1,000,000 units, the cost plummets. The estimate is $300 or possibly even less per unit at that kind of scale.
Wow. Where do the big savings come from?
Economies of scale on the components, that thermal core. Maybe $500 low volume, potentially $100 less high volume, or using cheaper far-IR sensors, regular cameras. $50 down to $10, $20.
Oh.
Radar or PIR. $50 down to $5, $10. The processor chip. $100 down to maybe $20, $30. The satellite modem is a big one. $300 down to maybe $100 if they get specialized IoT pricing for a massive order.
Right.
Solar and battery. $100 down to $50. The rugged box and bits and pieces. $100 down to $20, $30. You add it all up, and getting below $500 seems quite achievable with mass production.
That really puts it in perspective. Significantly cheaper than some existing systems, even early versions.
Yeah, the comparison to Lockheed's span sensor around $1,000 early on is interesting. This could potentially be more capable and much cheaper at scale. There's even mention of a stripped-down version, maybe no thermal camera, for under $100 in huge volumes.
Or lower risk areas, maybe. That tiered approach makes sense.
Okay.
But making millions of these, that's a huge manufacturing challenge, right?
Or massive. You'd need serious manufacturing partners, probably tapping into those big commercial electronics supply chains. And the testing. Rigorous quality control is non-negotiable. Every unit has to be waterproof, temperature-proof, reliable.
And deployment. Getting millions out there.
Huge logistics challenge. Specialized teams, maybe drones or helicopters like we mentioned. It's a vast undertaking.
Almost like seeding a forest with tech.
Kind of, yeah. And maintenance. Forget about it for individual units. You design for a certain failure rate and just replace them with new deployments. Software updates might be possible over satellite, but you want that initial code to be rock solid.
What about environmental issues, like leaves covering the lens, snow?
Real concerns. Falling leaves, snow buildup. Could block sensors, maybe a tiny heater or a shaker mechanism, but that adds cost and power draw. Wildlife, too.
Chewing on them.
Could happen. Or covering them in mud. So good camouflage helps, maybe deterrence in the material itself. You have to accept it won't be 100% perfect detection, 0% false alarms, but the density of the network makes it very hard to sneak through undetected.
High probability of detection, not a guarantee. Okay, zooming back out. What are the core trade-offs here? How does this hybrid sensor approach stack up?
It's always that balance. Power use, detection range and accuracy, cost, durability. Each sensor type has pros and cons. Visible light cameras. Great detail in daylight, struggles at night or in fog. Thermal. Excellent day-night heat detection, good range but higher cost, can struggle in heavy rain.
Radar.
Radar sees movement through stuff, great in all weather but no image. PI seismic. Super low power triggers, but short range, specific limitations like needing line of sight for PIR or ground contact for seismic.
So no single perfect sensor.
Nope. Which is why the hybrid approach makes so much sense. Use each for its strength. Low power triggers wake the more capable sensors like thermal or radar. AI filters the noise. You get redundancy, better all-weather performance, fewer false alarms.
It's layering the capabilities.
Exactly. It's more complex, yes, and maybe a moderate cost per unit, but the overall effectiveness in a tough environment like a forest could be dramatically better than relying on just one technology.
So, wrapping up, is this low-cost forest surveillance network really feasible, combining all these commercial and military tech advances.
The signs point to, yes, it seems feasible. The core technologies exist. Unattended sensors, SATCOMs, data fusion. It's been done, just maybe not at the scale and cost point yet. But the trends are heading there.
Driven by military needs like DARPA pushing for low-cost sensors and also this global interest in smart borders.
Precisely. And as volumes go up, costs come down. We've seen it with GPS, drones, thermal imagers, a known pattern. Imagine a sort of digital tripwire fence detecting threats in real time.
And countries like India are already looking at smart fencing sensor grids.
Yeah,
The demand is there.
absolutely. The need is clear. So the logical next step would be run a pilot project.
Yeah, test it out. Deploy maybe a few thousand in a specific challenging area. See how they really perform before going massive.
Makes sense. There are still big hurdles, of course, the deployment logistics we talked about, managing all that data, ensuring a fast response capability.
True, detection is only part of the puzzle. But the potential payoff, better security, safer personnel, is huge. It really does feel like a convergence point.
Military reliability meeting consumer tech affordability, creating this network of electronic sentries. It does blur the lines, creating this constant digital awareness. It's definitely a fascinating concept.
It really is a lot to think about there.
Indeed. And that brings us to the end of this deep dive.
But stay tuned. Join us next time for weekly AI news that's coming your way this Monday. We'll cover all the latest breakthroughs in artificial intelligence. Until then, keep exploring.